Welcome to solverfy.
This problem, we're given the following data set, everything in black, and we're also given that the expected regression equation for this problem is that y hat equals 1246.67 plus 7.6x. So I went ahead and calculated all the y hats, all the predicted y values for each of the given x values, and we'll use this later on. The first thing we're asked to do is come up with a point estimate that shows 500 units must be produced next month, or what the point estimate for the mean total cost for next month would be if 500 units must be produced. So what that means is that our y hat is going to be dependent on x equals 500. So if we go back to our regression equation, that would be 1246.67 plus 7.6 times 500. And with this, we get a value of 5,046.67. So this is our point estimate. And now we are asked to come up with a 99% prediction interval. So 95, or a prediction interval, is equal to the point estimate y hat star plus or minus t at the alpha over 2, the t test statistic at alpha over 2, times the standard deviation of the independent value. So let's first calculate this y hat star. We actually did that in the previous problem. This y hat star is equal to the y hat star in this situation. So we got 5,046.67. So this is equal to 5046.67. And now we need to come up with a t at alpha over 2. So our alpha is going to be 1 minus 0.99 because we are looking at a 99% confidence interval, is equal to 0.01. So this is equal to 0.005. So we will come back to this part later. Let's first calculate the standard deviation for the independence. So the standard deviation of an independent y value is equal to the regular standard deviation times the square root of 1 plus 1 over n plus our given x value, so x star, minus our mean x squared over the sum of the difference between each of our individual x values and our x bar. So first, let's calculate the mean of our x's. So the mean of our x's is going to be equal to 400 plus 450 plus 550 plus 600 plus 700 plus 750 divided by 6. And we get an x bar of 575. So this over here, and this is 575, and this is 575. And we know that our x star is equal to 500. So 500. And we know that we have 6 elements in our data set. Our n is 6. We know what each of the individual values in our data set are. All we need to do is come up with a standard deviation. The standard deviation is equal to the square root of the mean squares due to error. I'll do this on a different page. Mean square due to error, and the mean square due to error is equal to the sum of squares due to error over the number of elements minus 2, and the sum of squares due to error is equal to the sum of each individual y value minus the predicted y value at that point squared. So we already discovered the predicted y values over here, and we just did that by plugging in all these x values into that x. So we just have to take the difference between these actual y values and our predicted estimates. So this is going to be equal to our first example, 4,000 minus 4286.67 plus 5,000 minus 4,666, 666.67, and so on and so forth until you get to the end of the data set. And then we get a sum of squares due to error equaling 233,333.33. So now that this is the sum of squares due to error, we can plug that in here. This is 233,333.33. That's a lot of threes. And we have 6 elements in our data set, so 6 minus 2 is equal to 4. So we get a mean square due to error of 58,333.33. And now, to find our standard deviation, we just have to take the square root of that. And the square root of 58,333.33 is equal to 241. To 241.5229. So now we can plug this into our estimate here. So I'm going to delete that. And we just got a value of 241.5229. So this is equal to, I'll just write it out in cleaner terms, times the square root of 1 plus 1/6 plus 500 minus 575 squared over, and now on a different page, let's calculate this value. Sum of each of the individual x values minus the mean of x squared. So this would be, since our x bar is 575, 400 minus 575 squared plus the next value is 450. 450 minus 575 squared, and so on and so forth till we get to the end of our data set. And then we get a difference, a sum of squared differences equaling 93,750. So here, 93,750. Finally, we come up with a standard deviation of the individual value equaling, where is it? 267.5, approximately 267.5. And now we just have to plug that into this formula after we find our t value. So t of alpha over 2, and our alpha, this is equal to t of 0.005. And we have to find a p-value associated with this. And since we have 2 degrees of freedom, and our degrees of freedom, our degrees of freedom is n minus 2. Since we have an n of 6, this is equal to 4. So with 4 degrees of freedom and t statistic at a 0.005 alpha over 2, that is equal to 4.604. So now we can find a 99% prediction interval, which is equal to our test statistic of, or our point estimate of 5,046.67 plus or minus 4.604 times the standard deviation of the individual data point of 267.5. And then we get a interval of 3,815.1062, sorry, to 6,278.2338. So this is our 99% prediction interval for the total cost for next month. And now we're asked in part C, in part C, to come up with or to figure out whether the manager should be concerned about incurring such a high total cost for the month. So they find out that the actual total cost, their Y value, is equal to 6,000. Should they be concerned? And no, they should not be concerned. No, they should not be concerned because our interval contains the value 6,000. 6,000 goes in here because we are 99% confident that the true prediction of next month's production cost is between 3,815 and 6,278, and 6,000 lies between those two values. Manager should not be